The Apollo 17 mission visited the the basaltic Taurus Littrow Valley between the North Massif and South Massif Mountains. And this LROC image shows the South Massif mountain at the lower left. North Massif is just out of field of view at the top, and the actual landing place spot of the LEM is out of field of view to the right. In the center of the image is the light mantle deposit, a landslide deposit found at the base of the South Massif. And visiting and sampling this deposit was one of the main scientific goals of the Apollo 17 mission. This allowed investigation of the effects of a lunar landslide on the samples, and also allowed a sampling of material from the upper reaches of the South Massif that would have been otherwise unavailable to the astronauts, inaccessible to the astronauts. The X in the spot there, the X in the mantle shows the location of sampling station 3, which is where the double drive tube 73001-002 was collected, and it sampled this light mantle deposit to a depth of about 60 centimeters. We examined polished grain mounts of multiple size fractions of a less than 1 millimeter fraction of both 7001, 7002. We looked at about 24 different depth intervals. Here our data are summarized for the 1,000 to 500 micron fraction, and those are labeled F for finer. They're compared here to data for the coarse fines, the 10 to 4 millimeter coarse fines that were handpicked out during preliminary examination by Juliana Gross and examined and classified by XCT by Scott Eckley. And those results are published by Gross et al. And available on the curatorial website. These results show that both of these fairly coarse materials are dominated by regolith breccias and impact melt breccias. In the coarse fines, they're a little richer in Maya basalts than the finer materials, and our 1,000 to 500 micron fraction is fairly poor in Maya basalts and richer in highland igneous fragments and in monomineralic fragments. And with decreasing grain size all the way down to 20 microns and below, monomineralic fragments, agglutinates, and glass fragments become more important than they are in these coarse fractions. Now I'll be summarizing some of the sort of lithologic highlights that we found. First of all, although we found not a whole lot of Maya basalts in this highland-dominated deposit, we did find a wide variety of textures. The basaltic materials range from quickly cooled vitrophyres all the way to coarse grain materials. They range from ilmenite-rich to ilmenite-poor, in other words, titanium-rich to titanium-poor. Some have olivine, some don't. Some are silica-bearing, and some are not. And here are a few SEM images to show those ranges. Here's one of our quickly cooled samples. You see very fine ilmenite needles, quenched crystals of ilmenite. They have dark cores, which is armalcolite. That's an iron titanium oxide discovered on the moon, named for the Apollo 11 astronauts. It has a higher titanium to iron ratio than ilmenite does. That's why it's darker in backscatter electrons, and it indicates that you have a very titanium-rich melt, especially when it crystallizes early, like as it did here. In contrast, here's a sample of the very blocky, coarse ilmenite grain, showing that this material cooled very much more slowly. And we also have a rare type of, also first discovered in the Apollo 17 deep drill core was a VLT, a very low titanium basalt. And this little fragment is a possible candidate for such a sample. Has like accessory ilmenite and strongly zoned pyroxene zoned to very iron-rich compositions, very similar to the quad plot shown in the lower right there from the literature, showing a range of compositions in VLT basalts. One thing that was a bit of a surprise, at least to me, was that we found a bunch of felsites, very silica-rich materials, or essentially granites. This is a coarser grain sample. It's with fairly coarse silica, potassium feldspar, and sodium-rich plagioclase. And as typical seen and these samples typically have finely intergrown potassium feldspar and silica. Here's a sample much finer with an intergrowth on a much finer scale mostly an intergrowth of case spar and plagioclase, with some also those very bright grains or iron-rich pyroxenes. This sample was analyzed at JSC by Timmons Erickson, who did EBSD, electron backscattered diffraction, and found that there are two polymorphs of silica in this sample, both tritonite and quartz. It also has these common features of finely intergrown K-spar and silica. And also we've seen in these samples that K-spar has weight percent levels of barium oxide. The sample was also analyzed at JSC for water contents. The contents is analyzed by nanosims, reported by Shimizu et al. The K-spar, plagioclase, and tritonite also have ppm levels about an order of magnitude less than you would see in a comparable microperthite from the Earth. Also of interest, we found several plutonic samples that have spinel. Spinel in lunar samples is also often of interest. It's a possible indicator of a sample from very low depths. We found 5 northacitic rocks with spinel, and one interesting dunite with very primitive mineral composition shown in the red box with I think it's AN97 and FO93. That sample is shown in this slide here with the isolate plagioclase is sort of an isolated grain there shown. It's AN97, all embedded in very phosphoritic olivine. And the spinel is also very magnesium rich, which is unusual for lunar samples. And it's magnesium and also very luminous with a very small chromium number. Those compositions are shown on this plot. So on the left shows the composition of the olivine compared to other dunites and plutonic samples. And it plots in that blue oval there, distinct from other Apollo 17 olivines. It's calcium poor and very magnesium rich. The plot on the right compares the spinel compositions to spinels found in other dunites, and it plots down that's that represented by that green X, very low chromium number, very high Mg number, similar to those found in pink spinel anorthosites, but not dunites. And also, unlike other dunites, it's not brecciated and it doesn't have symplectites. So it is possibly a new rock type. Finally, to sort of recap what we've heard before, we're sort of expanding the range of known lunar rock types by sort of a role reversal. We've heard Chip talked about a basaltic impact melt. Typically, basalt impact melts are of highland origin, but we have a possible basaltic one. And the previous talk showed that also. And we also have two samples of MG sweet volcanism. And one was reported by Chris Yen, that's shown on the left, and the sample we found that was talked about by Chip is shown on the right. Similar textures, but not exactly the same. There are some features in the sample reported by Yen et al. That we don't see. And then here's a fairly higher magnification close-up showing the similarities of the matrices and those very magnesium olivine phenocrysts. So in conclusion, like most lunar drive tubes, our sample contains thousands of lithic fragments, exception probably being the Shorty crater glass-rich drive tube 74001-002. And this sample expands the range of known lunar rock types and increases our inventory of very rare rock types. And this demonstrates that regolith cores should be the part of any lunar sample exploration program because they yield quite a treasure trove of good things. Thank you.